Hello students, welcome back. Now let's talk about sections 5 and 6. Even though they are not directly related to this course, they're numbers too, so let's talk about those. Real numbers. Again, let's classify like these: algebraic, order, and some geometric properties. Algebraic properties. Yeah, we have all those. All those work out. Order properties, we have linear order, and the ordering preserves the addition and positive multiplication. Now, what if I multiply a negative number? We have to flip the direction of the inequality. Can you prove that? Okay, let's prove that. So let's begin with this. A times C is less than B times C. C is positive. Alright, and then let's use the first property. We just used the second property here. Now let's use the first property. AC is less than BC. And then here, let me subtract both by AC. And then subtract both by BC. Okay, and then what do you do? Let's see, too much space. Okay. Oh well. Okay, alright. AC minus AC, that's gone, so negative BC is less than, and BC minus BC gone, negative AC. That's what I got. So what do you have? B times negative C is less than A times negative C. And isn't that what we wanted all along? Yeah, all I have to do is flip the inequality and that's it. So here we go, we have the conclusion. We have the desired computation. And one more. Okay, now, exactly the same as the conclusion that we wanted all along. Okay, so much for order properties. How about the third property, completeness property? It's basically a geometrical property, or completely fills out a line. You see, the order property says R is linearly ordered. So is Q and G, as a matter of fact. So are Q and Z, as a matter of fact. But they both means all the integers and also all the rational numbers can be arranged on a line. But there are a lot of gaps there. For Z, there are big gaps. For Q, still there are many gaps. But R completely fills up. Another way to say the same thing is every bounded increasing sequence converges. Sorry about that. Unbounded increasing sequence, of course, goes to infinity. So also, another way to say the same thing is every non-empty set bounded above has the least upper bound. Oh, that's a bit too hard. let's not discuss it here. This is really an analysis material. So completely fills out a line. And as for bounded increasing sequences, think of decimal expansion or ternary expansion, binary expansion, things like those. Those are all valid because those are all bounded increasing sequences. Of course, there are more, but I mean, there are more, yes, true, but most of them are really difficult to visualize. So the expansion by a natural base is usually the best way to see the bounded increasing sequence conversion. Next, R is uncountable. Okay, here's a famous proof by Cantor. Suppose that the closed interval 0, 1 is countable. If so, we can list all the real numbers in this closed and bounded interval as a sequence xn, x1, x2, x3, and x4, and so on, in decimal expressions, x11, x12, x13, x14, and so on and so forth. And what you're going to do is to take these diagonals and then change these a little bit accordingly. We're going to define like this: y as 0.y1, y2, y3, y4, and so on, where yi is 2 if xi is 1. If xii is not 1, then yi is 1. So either way, xii and yi should be different. Then this number does not belong to this list. At some point, it'll have to cross a diagonal, and xii and yi are different. So we are looking at a different number. So y does not appear here. Wait a minute, if it's just one more, then why don't I just add one? Well, if it is just one more, you can add, but it's not one more, there are infinitely many more. I mean, this diagonal is one way, but there are other ways. You can take x11, x23, x24, and many more. x11, x23, x32, and x44, there are many more. As long as you get 2 or more on the same column, you can do this. So there are many, many more. You see, when we did this for rational number or other properties, densely distributed between any pair of rational numbers, there's at least one more rational number in there. I could select the average point here, but there are many, many more. If it is just 1 point, no, not 1 point, there are infinitely many more. Again here, I could have selected this diagonal, yes, but there are many, many more. You cannot just add one more and list it here and adjust the list. Even if you do, still a contradiction, but still, many, many more. Infinitely many more, uncountably many more. So there goes a contradiction. Consequently, this interval 0, 1 is uncountable. R is therefore uncountable. So those are well-known properties of R. And then how about some complex numbers? Okay, all right. Here's some algebraic properties. All those are standard. And then one more. C is algebraically closed. No matter what polynomial we select, it can be completely factored out. So if you have whatever polynomial equation with complex coefficient, all the solution, all the roots are back in C. So with polynomials, you cannot extend any further. It's algebraically closed. So we don't have to go any further than C. So if you say numbers, the granddaddy of them all is complex number system. Anything beyond that, we don't call those numbers. How about some geometric properties? C completely fills out a plane. Yeah, of course, X is a real number, Y is a real number. So horizontal X, vertical Y, so we have a plane. Complex conjugate corresponds to the reflection by the x-axis. So y goes to negative y. So y coordinate becomes negative. So distance from the origin is measured by the modulus. The absolute value is Pythagorean. And finally, the angular direction is measured by argument. So this is polar expression. Theta is polar angle, and x is arc cosine of theta, and y is arc sine of theta, polar coordinate. And cosine of theta plus I sine of theta happens to be exponential of I theta. So you can rewrite this into r e to the I theta, and then you can use all the properties of exponentials and exponent rules and things like those. Modulus is r, the Pythagorean distance from the origin, and theta is polar angle, or the argument. There's some further properties related to conjugate, and all these are elementary, but some of them are tedious. X plus yi becoming x minus yi, that's a conjugation. So if you take it twice, then minus another minus, so we get back to the original. And how about the modulus? X squared plus y squared, x plus squared plus negative y squared, that's the same. Square will kill off this negative, so they're the same either way. If you multiply these two and then do some work, then you're going to see that's the modulus. You'll see that. Just a bit of a work. And then all these, well, they're all true. And the proof is a bit tedious, especially the last one, but they're all true. So for addition, subtraction, multiplication, and division, you can always separate all the complex conjugate. Are these going to be necessary? I don't know. For this course, probably not, but, well, anyway, those are most basic properties of numbers, and lesson 1 deals with numbers, so let's talk about it, and here we go. Still, I'd like to keep those as an optional section, optional lesson. Let's come back. 99% of what we're going to do here will be about integers. As for rational numbers, well, each rational number is an integer over integer, so they're closely related. So rational numbers do show up, but they're always associated with two properties of integers. So up to here, we're going to use some, but these, not much, not very much.